Hi, this video is to help you give some advice on how to do homework number 2 about the simple linear regression model. I'll point out for you that to do this well, you should probably have the processed markdown file open, like I do right here. Shows you that if you run the instructions file without making any changes, what output and what pieces do you get to use for your analysis. Make sure you have that ready. Also make sure you read this advice document for how to write conclusions and how to do things. It's just sort of general advice about the problems. And I'm going to show you how to go through doing the homework, talk about the problems, dealing with the markdown file. So remember that you're going to need to use this set of commands and process it in the RStudio server. So what I will do is just click on that link, save the file to my computer, and it'll go to the downloads folder. And then what I'll do is I'll scroll up to the top of our course and log in to the RStudio web server, and I'll put in my username and my password. And I'll sign in, and I will get into my workspace, and I will bring that homework up to my files area, and we do that through upload. And I will go to my downloads folder and grab that homework markdown file, and in my downloads folder, there it is right there, markdown for homework 2, and bring that up to my files area, and there it is right down here, IRMD homework 2, and I'll click on it and it opens my homework right here in this window. And remember to change this, put your name right in here in line 19. We're going to need the knitter, the car, and the ALR4 package. Remember that if you haven't got those installed yet, you'll go over here to your packages area in the lower right and then install packages. The first problem is about snowfall in Fort Collins, Colorado. It's a data set that's in the ALR4 package. And what we're going to do is try to use the early first half of the snow season snowfall to predict the second half, the late snowfall. And in line 26 code block, we invoke and load the Fort Collins snow data. In line 31, we do a scatter plot of late snowfall on vertical, early snowfall on horizontal, no data smoothing mean function put in, and just the data. And if you look at the processed scatter plot, you'll see that the estimated straight line has been put in here. You can see that it's slightly upward sloping, and the question would be, is the underlying data creation system doing this? Is it a is it a positive relationship or a negative relationship? What's going on with the rate of change between early and late snowfalls? In line 34, it says that we're going to test the underlying slope parameter hypothesis, null hypothesis that it's equal to 0, against an alternative hypothesis that it's not equal to 0. And so in order to do that, you need to estimate the simple linear regression model with least squares, and we do that here in line 37. We make an R regression object called snowmod from the LM function, response variable late snowfall, X variable predictor variable early snowfall, and then in line 38 we give the coefficient summary so that you can see what we get. And you'll notice that came out right here. We get our estimated intercept, we get our estimated slope, beta 1 hat, we get standard error, we get t-statistic, and we get p-value. And in your markdown file, In line 41, I've specified the null hypothesis that you're to test. Beta 1 is equal to 0. And the alternative is that beta 1 is not equal to 0. Basically, the null hypothesis here says that there is no connection at all between the amount of snowfall that you get early in the season and the amount of snowfall you get late in the season. A slope value of 0 means there's a horizontal line, no relationship between the predictor and the response variable. The alternative hypothesis says that there is some kind of a relationship, and we need to find out what it is. In line 42 in the Markdown file, it says, put the value of the test statistic right here. And from the overhead notes for this course, you should realize that there's a t-statistic that needs to be put here, and it's beta 1 hat minus 0 over the standard error of beta 1 hat. And you can grab those values right here from the early row of the processed table. Here's beta 1 hat, here's the standard error of beta 1 hat, and the appropriate t-statistic is also in this output. And so I want you to put the value of the t-statistic right here, just type it right in this spot, go to the output table and put the p-value right here. Notice the p-value is given in this row also. This means p-value. So put the p-value there and then make the conclusion, like how I've been warning you in either the notes. So to do the appropriate p-values and conclusion, please read the lecture overheads. Please watch the video presentation and read the homework advice in order to do this correctly. For problem 2, we're going to use the mother and daughter data that has been described in the textbook and in my notes previously, and we're going to need to build a simple linear regression model explaining daughter's heights as a function of mother's heights using the heights data. And this section of code will pull out the estimated slope, the standard error for the slope, a t-statistic, the degrees of freedom, the p-value into different variables right here in R. And you can see me doing that here in the processed version. Here is the estimated intercept between the mother's and daughter's heights relationship. Here's the ordinary least squares slope between the mother's and the daughter's. Here's all of the coefficient, beta 1 hat, standard error beta 1 hat, t-statistic right here, 20.87. P-value right here is evidently nearly 0, and that's talking about, these values right here. So in RStudio, I'm making all of those things in this code block, and in line 76 we get a scatter plot for these data with the summary least squares green line going through there like this. And in problem 2a, I want you to test the null hypothesis for the slope coefficient, beta 1, beta 1 equaling 0, and the null hypothesis against beta 1 not equaling 0 in the alternative. I want you to put in the test statistic, the p-value, and do a test conclusion like I've taught you in the notes and in the advice document. You can grab the values for these by looking here at the output that was created, because here's beta 1 hat, here's the standard error for beta 1 hat, here's a t-statistic, and here is a very small p-value. You would put those things in right here and give me a conclusion. In line 87, the second part of this question, I am asking you to examine a slightly different hypothesis about the underlying data creation slope. Basically that it's equal to a value of 1, not 0. Alternative hypothesis that it's not equal to 1. And so what I've done here in this code block is done this t-statistic. I've taken the estimated slope, beta 1 hat. Remember I defined that earlier right up here in line 63. I've stored the value of the estimated slope, and then I'm subtracting off a value of 1 and dividing by the standard error. I'm in line 92 finding the p-value for that test using the t-distribution, the pt function for calculating a probability from a t-distribution. And in the processed output, you will notice I get that stuff. Here it is right here. Here is the t-statistic that you need for your test, negative 17.65. Here's the p-value for this test, very small, almost 0. And I'm asking you to put in those values here in line 97 for t and line 98 for p-value, and then make a full conclusion based off of what you've done. Remember, the question is whether the slope is significantly different than 1. And you got to realize what a slope of 1 would mean, and I've talked about it here in line 87. If mother and daughter heights were perfectly related, a mother who's an additional inch taller would produce a daughter that was an additional inch taller. And so there would be a perfect one-to-one relationship if height translated perfectly from mother to daughter. I want you to examine this hypothesis using the data. In problem 3, we go back to the Old Faithful data again, and in this code block we load it. We calculate the Old Faithful regression model. We save the estimated intercept in line 113. We save the estimated slope in a variable beta 1 in line 114, and we produce the estimated coefficients. The question of interest here is someone has just arrived at Old Faithful Geyser right after an eruption that was 250 seconds. I want you to give a 95% confidence interval for how long you think you might have to wait between what amount of minutes and the other amount of minutes for 95% confidence interval on the amount of time that you're going to need to wait for the next eruption. Here are 2 code blocks that might provide the answer. One of these code blocks is the correct thing to use, and one of them is incorrect. And I want you to look at the crucial items. The interval option, remember, is the thing that controls whether you're doing a confidence interval about a mean function, the average amount of time that you need to wait for the next eruption, or are you interested in an individual waiting time? How many minutes am I going to have to wait now? Not an average of a bunch of waiting times, but an individual one. You need to decide from the notes and from the readings which of these 2 is the right one to use, and then report the right one down here. What is the 95% confidence interval? How long do you estimate you're going to need to have to wait? Give the number of minutes and your boundaries. In line 140, I want you to see that if you put a backtick R and then use the y hat value that would have been last created here in 133, line 133, the value that you get is going to be placed in this point. You can see that on the processed homework right here. An individual has just arrived. Wait a minute, here we go. Note that if you want to use y hat or confidence limits in your written answer without retyping, you reference them by using the trick 78.2035. Well, where did this 78.2035 come from? It came from this part of the markdown file. This will go into the last code block and grab the value of y hat and place it right here in the output like you saw happen here. And this is another way to get the confidence limits pasted in. I'm not sure these are the right ones. You better check and make sure. What might be a good idea is to get rid of the code block that's the wrong one and only leave the code block that you want that gives the right answer. So one of the two of these code blocks is correct, one of them is incorrect. I would say get rid of the incorrect one and leave the correct one, and then this automatic typing of the values will be correct. In problem 4, we're going to study some countries and the relationship between the response variable of fertility, number of live births that are being given by females in that country, and per person GDP, basically the income and the wealth productivity of a country. What is the relationship between wealth and fertility? These fertility and wealth values have been modified by a base 10 logarithm. In other words, if the typical number of children per woman, the fertility was a value of 10, that would be a logarithm of 1. In problem in line 148, we invoke the data set from the ALR4 library. It's United Nations 1. In 4A, we compute the simple linear regression model estimate into a model object called M1, and we get the summary for it in line 155. When we look at our processed output, you will see the estimated intercept of 1.17 and an estimated slope of negative 0.2212, and this is all the output that was produced in 4A. There's no points for doing this, it's just part of the problem setup. In 4B, we give a scatter plot. There's no points for that, but here's the plot for it, the scatter plot command. And we see the scatter plot is right here. Pretty clear visually downward trend. Countries that have more income look like they have lower fertility. We'll have to check that more carefully with the rest of our work. Now we get to the work you need to answer and turn in. 4C. Do you think the true relationship slope, that means beta 1, do you think this is a negative value? Use a confidence interval to do your answer. And so I've given you the confint command for the estimated model, M1. Remember, M1 was produced right up here. And this will give you a reasonable range of values for the slope and the intercept. So let's see, where is it? For C, right here. Here's confint of the model. Here's the confidence interval for the intercept. I don't care about that one. I want you to use this confidence interval for the slope. And I'm asking you, do you think that the underlying data creation system has a negative value? Use that confidence interval in your answer. Please look at the advice document or the notes for how to do confidence interval conclusions. In 4D, you're asked to discuss the value of r squared and interpret it. And that is done through the value of r squared from the output right here where it says multiple r squared. So I want you to tell me the value of r squared, and I want you to interpret this using the percentage variation interpretation. And that's what you'll be doing here in 4D, putting the value right here and writing an interpretation in line 177 here. In problem 4E, we're imagining a country in the data set, a new country in the data set that has per person GDP of 1,000. What do you think the best estimate is going to be for the log of their fertility in that country? And so what you do is you use the predict command like I've done here, and you put in a PP GDP of 1,000, and you use the commands here to come up with an estimated log 10 fertility in line 191. This is going to be the y hat. This is found by plugging in 1,000 in for per person GDP. The model will take log base 10 of it and give you an estimated fertility, just like this. So obtain a point prediction for the fertility, the log fertility, and a 95% prediction interval. Notice the prediction interval is done right here with the option interval prediction. And in second part of this problem, if the interval is a 95% prediction interval for the log of fertility, how can I get back to fertility, which is in number of children units, not log of children units? And the answer is you need to take the lower limit and the upper limit of that confidence interval and use them as exponents. Raise 10 to the lower limit and raise 10 to the upper limit, and you'll be able to get a range for the 95% confidence interval for the actual number of children fertility for such a country. And you'll notice in the processed output you have done that right in here, where we take the results of the prediction interval and we take 10 and we raise the boundaries as the exponents, and you get the confidence interval that's right here for problem 4E. In problem 4G, we're going to talk about unusual residuals and cases. In the first part here in 4G, I'm asking about who has the highest fertility. And so what we've done is we take the data set and we use an ordering command. We basically reverse order so that the top of the data frame has the highest fertilities. And by using the head command, we obtain the first few rows of the top of this data file. And so you look at the countries that are there that have the highest fertility. We do a similar thing to find the lowest fertility. We order the data frame, and that will produce a small to big order, and the top of that data frame will have small fertilities. Which country has the lowest fertility? In the third part, I want you to look at the residuals for the regression model that we made. And so here I am going to, in line 231, I'm going to make a new data frame that has the old data and our residuals from our model. And then I'm going to order this new data frame according to the residuals. And so it is going to go in reverse order. So in other words, the biggest residuals, these would be fertilities that would be quite a bit bigger than what we were expecting from our model. I want you to give me the two that have the largest residuals, largest positive ones. And then in the fourth part, we create an ordered list where we have the most negative residuals at the top. And in the processed file, you will see these ordered files: fertility, lowest fertility, largest possible positive residuals, largest negative residuals. And I want you to be able to read these tables correctly and find and list the countries that I'm specifying. Let me know if you have questions about doing this assignment.